Welcome grade 12s, and today we're looking at our last bit of revision for this term, and we're going to look at paper 2, which means we're looking at chemistry. Now remember, in this year we've actually done a lot of chemistry, so we've done the organic, there's rates of reaction and equilibrium and acids and bases, and obviously we can't cover everything in this hour. So what we're going to do specifically is I'm only going to look at rates and extent of chemical reactions, I'm going to look at chemical equilibrium, and I'm going to look at acids and bases, okay? So a lot like we did last week, I'm going to give you some questions, give you a little bit of time to see how much you can answer, and then I'll go through them with you, okay? So let's see how much we can get done. Let's start with rate of reaction, and this is from a Western Cape prelim. And it says to us that Sarah wants to investigate the rate at which a reaction proceeds. Great. Places a beaker containing dilute nitric acid. So whenever we read, we always need to make sure we underline or highlight important information. On a sensitive balance in a fume cupboard. The sensitive balance is an electronic scale, and it's sensitive, so it shows small changes quickly. And we're just putting it in a fume cupboard because she's going to put copper metal in here. That means I'm going to create nitrogen dioxide gas or nitrogen monoxide gas. But I'm going to create a gas because it's an acid plus a metal. I'm putting it in the fume cupboard as a safety precaution in case that comes up somewhere along the line, okay? The mass readings of the beaker and the contents are recorded every 15 seconds from the moment the copper metal is dropped into the acid until there is no more copper metal present. So what they're saying to us at the beginning here is that the copper is my limiting reactant. So the amount of copper I use is going to determine how much product I get. So here we go. We've got the dilute nitric acid. They give us a reading. And then they say the reaction that occurred is represented by the following. So we have the copper plus the nitric acid gives us copper nitrate. This is the gas that's been released. And we recognize from this that that's why it's in a fume cupboard, because of the nitrogen monoxide. But whatever mass, however this reading on the scale changes, that's telling me how much nitrogen monoxide is made. Okay, so then it says to us that she gets a whole bunch of results. So here's our set of results, okay? So from 0 to 150 seconds, mass of the beakers, and then they give us the decrease in mass. They make it very easy for us. We like that. Okay, now we've got a couple of questions. Give a reason why the mass of the beaker and the contents decrease, and then use the values in the table and calculate the average rate. Not really very difficult, so I'm going to give you a minute to get that, okay? So you're telling me why does the beaker change mass, and then calculate the average rate, okay? So you have a minute. Your minute starts now. All right, grade 12, so let's see how you did. So the first question, of course, was why is the mass of the beaker and contents decreasing? There's actually a couple we could accept, but the best one is the fact that NO gas is produced. All right, and because the NO gas is produced, that's allowed to escape. Or you could tell us it's not 100% great, but it's all right. It's an open system. A gas is produced and is allowed to escape. The whole point here is that we recognize the gas is being produced, okay? That's the important part here. Now they say to us, use the values in the table and calculate the average rates in grams per second, that should be superscript, for the whole 150 seconds. Now, we want average rate, so we're going to go, well, I want a rate. And remember, we define rates as the change in concentration of either the reactants or the products per unit time. So we've got to now look at what this rate, and we're going to do the rate at which the gas is produced. So that means what I'm going to do is I'm going to go the change in the mass of divided by the change in time. All right, so now we go back to our table and we go, either I can do 114 minus 108,3, but why, when they told us that the decrease in mass was 6,3 grams? It's given to us already. It's actually a really simple question. We just sometimes get a little bent out of shape because it's something new. So we have 6,3. We're going to divide it by 150. Okay, and now I just want to double check that I've got the right answer. So remember, we use our calculators and we're going to go 6.3 divided by 150. There we go. Remember, no fractions, so we change it and it gives me 0,042. Okay, so, how many of you are screaming at the TV and going, hang on, wait, Tracy, there's a problem? Because when we look at this and we go back here and we say, well, if I take the 6,3 and I take 150 seconds, there's a problem. What has happened after 105 seconds? The reaction is actually stopped. So I really should take this time, they've been a bit mean here, this time here should actually be 105. And now hopefully some of you are going, yeah, I knew that. You just weren't paying attention. Okay, as you can hear, my head's a little full of cotton wool, so sometimes we don't always get things right. So it's 0,06 grams per second. Okay, now let's move on. Now they give us a graph. This is such a nice graph, guys, because it's done on graph paper. It's actually really easy to read. You can see the values really nicely, and we like it. And we go, okay, so what do they want? So here's our graph, and then they say to us, there's two questions here. They say, three actually. Give a reason for the shape of the graph from 105 to 120 seconds. So that's the first one. Give a reason why the rate increases and then why the rate decreases. And then this is actually 1.5. Explain your answer in 1.4.2 in terms of collision theory. So, 3 questions. I'm going to give you 2 minutes. I'll go back to the graph in a second. All right, so those are the 3 questions I want you to do for now. All right, I'm giving you 2 minutes, and your 2 minutes starts now. Okay, Grade 12, so let's see how you did. All right, I know I'm giving you very little time, but we're going to work at pace. If you can manage to work at this pace, you'll be fine for your exams. So now it says, give a reason for the shape of the graph from 105 to 120 seconds. So now we look at the graph and we go, well, at 105, which sits, so there would be 110, 105 is around here somewhere. So they're looking at this point. Now, if we look at that, the graph goes flat. Okay, that tells me that no more NO is being produced because the mass remains constant. So if the mass remains constant, okay, the reaction has gone to completion, or the reaction has stopped. Okay, it's finished. And remember, they said right at the beginning that they kept timing until all the copper metal was gone. So the reaction is stopped. Nice and easy. Then they ask you to give a reason why the reaction rate increases between 0 and 30 seconds. So we look at this and we go, well, if we look at 0 and 30, so at this point, the graph is getting steep, it's getting faster, and we would actually expect it to start slowing down because we're using up the reactants. However, if we go back to the reaction, so we go back to the equation, which we have over here, okay, so we go back to the equation in the question, so we go back over here to the equation. Look here, in the equation, delta H, okay, it's the wrong way around, it should have said this. It's an exothermic reaction. So what happens here is that as the reaction proceeds, we're actually giving off heat. Okay, so the reaction is getting hotter. And if the reaction gets hotter, then the reaction rate increases. So the temperature is increasing. So the temperature increases. Okay, why? Because it's an exothermic reaction. So it gets faster. Then the rate decreases between 45 and 105. So now we go, well, between 45 seconds, which is this part here. So now we're looking at this part of the graph, and you can see it's slowing down. Now it starts to slow down because now we've used up reactants. Okay, why? Because the reactants are being used up. Okay? The reactants are getting less. Okay? Or you can tell me the concentration of the reactants is decreasing. Either way. Now they say explain your answer to question 1.5.2 in terms of the collision theory. This means, okay, this is the whole thing about collision. So the particles are, the number of particles, that's a better way, not the particles, all right? It's always important to write exactly what you mean. So the number of particles, number, not numbers, number of particles is decreasing. Okay? That means, therefore, there are fewer effective collisions, okay, and the rate decreases, okay, so there are fewer effective collisions and the rate will decrease, okay. You ready to tackle the last one? So, here we go. We need this. The reason why I've got this is we need the reaction again, so this is actually quite important, all right, and now my question says to you, calculate the mass of the copper used in the reaction. Okay, I want you to remember that what we know is that I create 6,3 grams of the NO. And now I want you to calculate how much copper is created. Okay, so I know we're going to go a little bit over now, but this is important. So now I'm going to give you a quick, I'm going to give you a minute, quick, 1 minute, calculate how much copper I used. All right, your time starts now. All right, grade 12s, I know I didn't give you enough time, but I'm hoping you started on the right track. Now, remember, with a question like this, I'm looking at mole ratios. Okay, this is stoichiometry from grade 11, which is why I needed you to do this. So once I know how many moles of NO I've got, I can work it backwards to get the amount of copper. So let's go back here. All right, and now we want to calculate the mass of the copper used in the reaction. So first thing I have to do is work out the number of moles of NO. Now, the number of moles of NO is mass over molar mass. The mass we had is 6,3 because that's what was lost. And the molar mass of nitrogen monoxide is 14 plus 16. All right, 14 from the periodic table, and so is the 16. It's the atomic masses. So I have 6,3 divided by 30, which gives us 0,21 moles. Now, the whole point of this is to work out how much copper I'm going to have used. Now, copper, the number of moles of copper is going to be 0,21 times by the mole ratio. So we go back here and we times it by the number of moles of copper that we want, which is a 1 from the copper, over how much nitric acid nitrogen monoxide we have, which is 4. Okay, so let me put it this way. This might be easier for you to see where I'm going. If I go copper to NO, and that's just horrible, it's 1 to 4. Okay, so the copper to nitric acid NO is 1 to 4. I'm looking for the X to, sorry, I've got, it's 1 to 4, just go, it's 1 over 4. Let's just take it as that. It's 1 over 4. That gives me, and I've put it in scientific notation because it's easier, so that's how many moles of copper. Now I can work out the mass, because mass is number of moles times molar mass, which is 5,25 times 10 to the minus 2, and the mass of copper, which we look up on our table, is 63,5 and 3,33 grams. Okay, so I'm pretty sure you need a break, because I know I do, so I'll see you in a couple of minutes. Okay, grade 12s. Now we've got over our little stoichiometry moment. Now we've got to hit chemical equilibrium. All right, you're going to get these. I'm sorry, it's one of those things. So let's dive straight into our question. And it says carbon monoxide gas plus oxygen gas are placed in a closed container. They're allowed to react to form carbon dioxide. The balanced equation for this reaction is this. Now we like the balanced equation, so that's important. Okay, it's balanced, great. You don't have to worry about it. The graph below shows concentration changes of reactants and products for this reaction over time. Use this information and answer the following questions. So now, before you even look at the questions, okay, the best thing you can do is work through the graph. So the first thing you go is this here, those points there, that's the start of the reaction. The forward reaction increases, we get more CO2, we get less O2 and CO, which we expect. At T1, so at this point over here, this is equilibrium because all the concentrations remain constant. Then something happens at T2, and we look at it and we go, well, if we look here, that only changes a little, that changes a little, that spikes. That means I added in the CO2, that's part of the CO2 line. You see, it's part of this line. So I added in, so we're going to write a little note for ourselves. So at T2, we probably increased the CO2. Okay, that's my thought. Then, okay, and T1 is equilibrium. Okay, T2, we added in CO2. We get to T3, and look here, it goes straight again. So T3, I reached equilibrium again. And now at T4, there's no spikes. So probably at T4, I changed temperature. Okay? Now, because the original reaction doesn't tell me whether this is exothermic or endothermic, I can't say whether I increased or decreased my temperature. But what I can say is I favored the forward reaction because I ended up getting more CO2. So whatever I did to the temperature, I favored the forward reaction. Okay? Great. That being said, we go to the first questions. This is explain the term chemical equilibrium. I'm not going to give you time to do this. This is a definition. And what we want is the term equilibrium is when the rate of the forward reaction, okay, so the rate of the forward reaction equals the rate of the reverse reaction. Okay, so that's something you should know because it's a definition. Now they say to us, let's go here. Now we've got a couple of questions, all right? And it says at which time interval is the reaction at equilibrium? Then, does the forward or reverse reaction have faster reaction rate? The temperature is decreased at T4. What does that mean? And then you have to explain your answer in 2.4. Okay, so we've got 4 questions. I'm giving you 2 minutes, and your time starts now. Time's up, grade 12s. I can just hear the grunts. Josie, we're not done. It's all right. It's all right. Okay, so the first question we asked you was, at what times did it reach equilibrium? Okay, so now we look at it and we go, well, let's go back to the graph. Now, this one I have got here isn't all written on, but that's okay. Remember, it's the times where it goes flat. So at T1 and at T3. So that was easy. All right, so here we'd say T1 and T3. Then it says, does the forward or the reverse reaction rate have a faster reaction during the interval T2 to T3? So now we go T1 or T, okay. I'm not really sure what we were, oh, there we go. Does the forward or reverse reaction have the faster reaction rate during the interval T2 or T3? Okay, so let's go back here. Apparently my memo is not working so well today, but that's all right. So T2 and T3, and we go, okay, so which one has the faster reaction rate? And we go, well, actually, to start off with, it's going to end up being the reverse reaction because I added in CO2. So as the reverse reaction slows down, the forward reaction speeds up. Okay, so when we look at this and we say to ourselves, well, which one has the faster reaction rate? Does the forward or the reverse reaction have the faster rate during the interval? It's going to be reverse. Okay, now it says the temperature is decreased. Is the reaction exothermic or endothermic? So we go back here and we say, fine. Remember I said at T4, that's a temperature change. temperature was decreased, and we look at our graph, but the temperature decrease favored making product. That means I favored the forward reaction. And remember, when I decrease temperature, I always move towards the exothermic reaction. Okay? So if by decreasing temperature, I make more product, that means the forward reaction, making product, is the exothermic reaction. So here, is it exothermic or endothermic? Well, it's exothermic. Now they ask you to explain it. So now we've got to do this. Okay, now watch. The concentration of the CO2 increased. Okay, increased. So we saying what happens. Okay. Therefore, the forward reaction was favored. Okay. A decrease in temperature always favors the exothermic reaction. Therefore, the forward reaction is exothermic. Okay. Not so bad. Bet you are waiting for the horrible question, and here it comes. Okay, so here's our situation. We have our equation, and now they say to us, well, first of all, what change was made at T2? And we spoke about that earlier, and we said, well, the CO2 was increased. Okay, so we do that. How does the change made at T2 influence the value of the Kc for this reaction? All we did was change concentration. It remains the same. This is so important. Okay, please remember, the only thing that changes the Kc value is temperature. And at T2, we didn't change temperature. Okay, this is the question you're looking for. Initially, 63 grams of CO and 9,11 grams of O2 are placed in a 2 decimeter cubed container at equilibrium. The concentration of the CO2 is 0.15 moles per decimeter cubed. Calculate the value of the Kc for this reaction. So remember, we've got CO plus O2 going to 2CO2 because that needs a 2. And there we go. So that's my balanced equation. You don't need to go back to it here because it's there. It's all gases. There's the question. Okay, I'm giving you 3 minutes, and your time starts now. So, grade 12s, how far did you go? I can hear the groans. Okay, so let's just see. Now, this is a little bit of a tricky question, which is why I put it in, because we've done really simple KC calculations up till now. The only part that makes this a little bit more tricky is the fact that they gave us the initials in grams. So the very first thing we have to do is change those to moles. So the number of moles of carbon monoxide, which is mass over molar mass, is 63, and carbon is 12, oxygen is 16, so it's 63 divided by 28, which is 2,25. Okay, then we need the number of moles of oxygen, so that's also mass over molar mass, so that's 9,11, and it's O2, so that means it's going to be 2 times 16 divided by 32, which gives me 0,28 moles. Now, from here, I can do my equilibrium table, which is what we want. So now we've just calculated that we had 2,25 of the CO, 0,28 of the O2, and we always start with 0 CO2. They told us in the question that at equilibrium, we had 0,15 moles per decimeter cubed of the CO2. Here again, they've been a little mean because we need equilibrium moles, but they told us that the container had a volume of 2 decimeters cubed. So remember, concentration is number of moles over volume. So number of moles is concentration times volume. So if I take the 0,15 times by 2, that gives me 0,3. That's how many moles of CO2 I've got. So now we've got the number of CO2. Now we're going to work out the equilibrium constant the way we've done any of them. So now we go back to our table and we go, fine, I had 0,3 moles of CO2. Remember, I started with 0. I made 0,3, so now my change is 0,3. Remember, my ratio mole and my row and my change row must be equal. They must be multiples of each other in terms of your ratio. So CO and CO2 are a 2 to 2, 1 ratio. That's the same as a 1 to 1 ratio. So I can just put 0,3 there. We're happy. The oxygen is 1, CO2 is 2, that's a 2 to 1 ratio, and I have twice as much CO2 as O2, so I need to divide the 0,3 by 2, that gives me 0,15. Now we go down and we say, fine, I used up reactant, so I'll go 2,25 minus 0,3, and I have 1,95 left over. I go 0,28 divided by 0,15, and I left with 0,13, but it's a KC expression. That means I need to have in moles per decimeter cubed. Remember, my volume was 2, so I need to divide this by 2, and we get 0,975. I need to divide this one by 2, and I get 0,065. I now have equilibrium values. We're happy. We need to do our KC expression, and KC is the products. Okay, CO2 squared, because it's 2 CO2 over my reactants, and that's CO also squared, because it's 2 CO plus O2. We write in what we know. The CO2 is 0,15 squared, and the CO is 0,975 all squared. This is 0,065 not squared, which is nice, and we get an answer of 0,36, which tells me that we have a lot more reactant than product. It doesn't actually matter. We can see it from the equilibrium concentrations. Once we've got the number of moles, so the trick to this question was the number of moles for the CO and the O2, grade 12s. That was the trick. Once we had gotten that at the beginning, all the rest is exactly as we've done it. And KC values, I'm afraid, are practice, 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 grade 12s. No way around that one, okay? So, now that all our brains are fried, because we've worked really hard, we're going to take a short break, and when we come back, we're going to go through an acids and base question. So I'll see you in a couple of minutes. All right, grade 12's last little bit, okay? So now we're looking at, okay, so now we're going to look at acids and bases, and we've got I'm going to dive straight in there. Bottle contains dilute. That's probably important. So let's just do this. Dilute sulfuric acid of unknown concentration. Oh, I can hear the groans. Okay. In order to determine the concentration of the acid, the learner titrates the acid against a standard solution of potassium hydroxide. They give us the balanced equation. Yay, we like that. And the very first thing they ask us is to define the term dilute acid. I'm not going to give you time to do that. Remember, a dilute acid is an acid that ionizes, and you have to use ionize, that ionizes. Okay, let me spell that nicely for you. Ionizes only slightly in water. Okay? Guys, strong, that I'm so lying to you right now. It's a dilute acid. I'm giving you the definition of a weak acid. A dilute acid means that there is a low or a small number of acid particles per unit volume. Okay, I was busy giving you, I'm just checking you guys are awake. I was giving you the definition of a weak acid of per unit volume. Okay? Okay, good. Let's move on. So, we've done all of that. And the first thing now says, calculate the mass of the potassium hydroxide needed to prepare 300 centimeters cubed of a 0.2 mole solution. Okay, and then you have to calculate the pH of the KOH solution. So, what I'm going to do is I'm going to show you how to work out the mass of the potassium hydroxide needed, and then I'm going to give you time to do the pH because that's the important one. So let's go here and look at the mass. So concentration we're given is 0.2 moles per decimeter cubed. The volume we were told is 300 centimeters cubed. And we want little m. Now, there's an equation on your table, on your information sheet, which says concentration is molar mass, mass given over molar mass times volume. That's the equation we want to use. The thing we have to remember about this, first of all, is that my volume has to be in decimeters cubed. Now I need to work out the molar mass. So I'm going to take this off. And we're going to go back to our periodic table. We're going to work out the molar mass of potassium hydroxide. Potassium has a mass of 39, okay. Oxygen is 16, hydrogen is 1, and that's 56 grams per mole. From here, I can work out the mass needed quite easily because I'm going to use my equation. The concentration they told us was going to be 0.2. We want little m. That's 56. We know the volume's 0.3. So my mass is going to be 0.2 times 56 times 0.3, which gives me 3.36 grams. Okay, now the nice thing about this question is this actually stands alone. So to answer the next question with the pH, you didn't need to get this answer, which is actually really nice. Sometimes they don't do that, they follow on, but you didn't need it. So let's go to the next question, which is calculate the pH of the potassium hydroxide solution, assuming that the KOH dissociates completely. Okay, I'm going to give you, now it's 6 marks, don't stress about that, okay? I'm going to give you 3 minutes, because this is a really important question, okay? So I'm going to give you 3 minutes, your time starts now. Grade 12s, I hope none of you gave up and you kept going. So let's look at this. Now, we want the pH of a solution. And the thing here is that we were given a base. Okay, whenever we have a base, we know we're going to have to use the Kw value, all right? So the first thing we recognize is that potassium hydroxide, when it dissociates, is going to become K plus and OH minus. Because we assume complete dissociation, all of that changes into my products. That means that the concentration of the OH minus ions is equal to the concentration of my potassium hydroxide, because it's complete the complete dissociation and it's a 1-to-1 ratio. Then we remember that H3O plus times by OH minus must give me 1 times 10 to the minus 14, the ionization constant of water. So now we go fine. Once I've got that, we can go, all right, H3O plus. I know the OH minus is 0,2. We just worked that out. 1 times 10 to the minus 14. Great. Then we go 1 times 10 to the minus 14 divided by 0,2. That gives me the H3O plus concentration. 5 times 10 to the minus 14 moles per decimeter cubed. Now, remember, why am I looking for that concentration? Because the pH is the negative log of the H3O plus concentration. So that's where I've always got to go. Once I've got the H3O plus concentration, all I need to do is go negative log 5 times 10 to the minus 14. Okay, now I just want to remind you, because I know some of you struggle a little bit with this. So we're going to go, when we put on calculate, negative log 5 exponent negative 14, close your bracket, equal 13,130. So we have 13, let's take that away, go away, 13,3. Now it's a base, it's potassium hydroxide. We expect a high number. Okay, it's one of the group 1 bases, hydroxides. It's a very strong base. 13,3, perfectly acceptable. Okay, work through it step by step. Okay, we did that very quick. Almost done for the day. Now they say to us, okay, a bottle contains dilutes, we said. A list of indicators is given. Which one of these indicators could best be used for this titration? Well, we've got a strong acid with the sulfuric acid and a strong base with the potassium hydroxide. And through hydrolysis, we know that that is going to give me a neutral salt then, because they're both equally strong. So if we get a neutral salt, we need an indicator that will give me the correct, that gives me a pH range in somewhere around 7. Okay, so which indicator is best? Bromothiamyl blue. Why? Okay, and this is more the important part, so I'm going to give the explanation. So we're using bromothiamyl blue. Why? Because H2SO4 is a strong base, a strong acid. Potassium hydroxide is a strong base. Therefore, a neutral salt is formed. And the end point is approximately, okay, it's never exactly, pH equal to 7. Okay, so not 100%, but close to it. Okay, last question. Here we go. Now it says, during the titration, we find that 15 centimeters cubed of the KOH solution neutralizes 20 centimeters cubed of the H2SO4. Now they say, what is the H2SO4? Remember, that one was 0,2 moles per decimeter cubed. When we see this, this is a grade 11 titration equation. Na over Nb equals Ca Va over Cb Vb. Okay, balanced equation. Number of moles of acid, it's a 1-to-2 ratio, so that's 1 over 2. We want the concentration of the acid. We use 20 centimeters cubed, does not need to be converted. This was 0,2. That was 15. I don't need to convert the volume because both are in centimeters cubed. This one's a little more difficult mathematically. So CA, and we do our little, the 1 stays there. This becomes 0.2 times 15, all divided by 20 times 2. Don't forget the 2 in the front. And that gives me 0.075 moles per decimeter cubed. And now we all sigh relief and go, we're done. Okay, grade 12s. Don't forget, you are more than likely going to have organic chemistry in your June exam, especially if you're writing an external paper. Learn, learn, learn. Lots of calculations in what we've done in the last section with the rates, the equilibrium, and the acids and bases. Remember, in each of those, we can have stoichiometry from grade 11. Okay, all of the stoichiometry in grade 11 can be asked in this section, so make sure you learn that as well. Okay, more you practice, the better you get at it. The more you see that we can only ask you so many things. There's only so many ways we can ask a question. And don't forget, there wasn't a lot in these questions, but there's still theory, there's still definitions, there's still laws you need to learn. Make sure you know them. Okay, grade 12s? So I wish you all the best of luck, and then have a great July holiday. Use it effectively, and I'm sure I'll see you next term. And I'm done for today, so I'll see you next term.